So this is going to be a review video that goes over lesson 6. I know that we haven't all finished lesson 6, but I want to make it one cohesive thought so that we have some idea of how we got here. All right, and I'm going to be using some of the screenshots from week 7 instead of rebuilding everything so it doesn't turn into a 20-minute video. All right, so the idea here is that if you didn't understand something, or if you were uncertain of how something worked, or if you just need to go hear it one more time so you can write down everything, this is your chance to do that. All right, so we're going to be doing lesson 6, which is building quadratic functions to describe a situation. This is part 2. If you'll recall in lesson 5, which was part 1, this is where we built in a quadratic function where it fell from the top of a tower to the bottom of the tower. And we found that when we did that, the equation ended up being the distance is equal to 16 t squared, where t is the value of seconds. So 16 times the seconds squared. This is acceleration due to gravity. We're going to use that word several more times. All right, so let's go ahead and jump down here. So the idea here is that there's a cannon. It's 10 feet off the ground. It launches a cannonball straight up with the velocity of 406 feet per second. So I will build this image, but I will not sit here and calculate it while we're here because we've already done that as a class. All right, so what you're picturing is there's something that's holding a cannon up, right? This is my super technical picture of a cannon, right? And this is a cannonball. So the cannonball has to be smaller than the cannon. And we can draw an up arrow, so we know that the cannon is going upwards. All right, so this is a table, or I'm going to call it a table because that's the best way I can see. It is 10 feet high. This is my cannon. If you're in class already with me, I found a picture of a pumpkin shooter, so we can say that it shoots pumpkins for the fun of it because that's hilarious. Right? And it's going to shoot them at 406 feet per second. That is the speed, and since the speed also has a direction to it, we can also call this the velocity. Right, so speed and velocity are the same in this case because it has a direction. All right, so when we built the table, I'm going to just go borrow the table from over here. I will copy this one and paste it over here. Maybe. Copy this and paste. And it's not working. All right, whatever. We can build our table. So I will just refer back to it so that you don't have to sit here and watch me do the math. All right, so we built a table. We had 3 sections to this table, right? And that was my way of making nice straight lines so that I didn't have to freak out because my lines were uneven. It's not perfect, but it's better. So we have the seconds, right? That's the time. So that's t. We have the equation, right? So we're going to have 406 times t. And then we're going to have the distance. We're going to have the feet. And if you remember from class, it's a pretty classic science thing that if you have the distance is equal to the speed multiplied by the time. And that's an easy one to do because if I ask you if you're driving at 60 miles per hour and you go for 2 hours, most of you came up in your head that you go 120 miles, right? And most of you recognized this right off the bat, and there was no questioning of how you got there. So this is a pretty common math science idea. I'm going to go ahead and get rid of it so that you're not confused of why we have it, but it's just to remind you that distance is equal to speed times time. All right? So our time, let's do 3 different sets. So let's do our first one, which is 1 second. So at 1 second, we're going to have 406, the speed, multiplied by 1. 406 times 1 is 406. We're going to have 2 seconds to 406 times 2, 406 times 2. Or we can put it in parentheses like we were doing before. I can keep it consistent. And that should be 812. Again, if you don't know where I'm getting these numbers from, be sure to slow this video down, pause it, do your own math calculations. It should be pretty straightforward of where it's coming from, but if you're not sure why it's there, this is just the review video. I don't want to spend a whole bunch of time figuring out how to multiply something, but we know that this is our distance times speed. All right, so we have 406, and we multiply it by 3. And 406 times 3 is 1,218. All right, and we said, okay, that's great, but we forgot something, right? What did we forget? We forgot the table. We need to keep that in mind. So we need to remember to add the table. So in all of these, we're going to have to add a plus 10, right, for the table. So plus 10, so then our answer should be 416. We're going to do the same thing on here. We're going to have plus 10 for the table. And our answer, I can do this in my head, is 822. And then we're going to have plus 10 for the table. And our answer is 1228. All right? So these numbers right here, these are our expected. Right? This is how we would expect to get this answer. So we went ahead when we went back to our notebook and we put all these answers in and we calculated our expected equation. Right? And this was our expected equation. I think that's self-explanatory. The 406 is the velocity, multiplying it by time, and then we're adding a constant of the 10 feet that it's sitting off the ground. All right, so when we went to the next slide, here's our pumpkin cannon, by the way. So you can enjoy that picture. All right, so again, we did this already, and because this is a review video, I mostly just want you to understand the concept, so I'm not going to multiply everything out. But the table showed what our expected was, right? And what we found was when we graphed it, and I'll just draw a picture of what the graph looked like. When we graphed it, here's my graph. I am cheating on my graph and making it the fastest way I can, which is a rectangle instead of that. So when we graphed it, our expected would have looked like this, right? We started right here, and our expected was a linear equation that just kept going up, up, up. It's a roller coaster that always goes up. And then what we actually observed was something where we went here, but then it was starting to go underneath it, and maybe it wasn't following quite the same path, right? And this is what we actually observed. So the observed was less. And what you guys told me is that this was probably due because our equation didn't include gravity. Right? So we had to find an equation that did include gravity. So what we found was when we actually did the subtraction, right? So it says in our notebook, this is our notebook, it says write an equation to model the actual distance. If you get stuck, consider the differences. And we were reminded that difference is a result of subtraction, right? Again, if you are not sure about this, you should definitely go back and put it in there. So we looked at this and we have the predicted and the actual results, and we did the difference, and we found that we were seeing this pattern, negative 16, negative 64, negative 144, negative 256, negative 400. This pattern was the same as when we were dropping a ball off of the building, right? This was acceleration due to gravity. So we found that the observed, I'm writing in purple still, the observed was created by the expected minus the effect of gravity, right? So we have to subtract gravity because the cannon is shooting upwards and the actual graph is going, the gravity is pulling it downwards. So gravity is negative because it's pulling it downwards. So what we calculated in is we found that 406 t plus 10 was our expected equation. And then we subtracted 16t squared, which was the result of gravity, right? This is the effect of gravity on it. I'm going to take out the word effect. So we have this is gravity, and this is our expected. If we drew a line under it again, our expected, here's our expected equation. And then the results due to gravity, which is giving us our purple right there, we're subtracting out gravity. And this is the most important thing that you can think of in this lesson, right? We found that we could put this equation together. We got 406t plus 10 minus 16t squared. So today what we did is we looked at an actual cannonball, right? We looked at this new equation. And I'm going to give you this on Wednesday, so for those of you who made it through there. But when we graphed this equation, it gave us a parabola, right? It gave us that arch. It gave us a height like this. So if I'm going to graph it on my equation, it gave us this arc that looked like this. This was our result. I'm going to put this in. I'm going to do it with lines. Right? When we put this on the graph, this was our result. Bothers me so much. That's close enough, right? So when you guys multiplied it out, what we found was this was our max. Right? This was the max height. Right? When it got back to 0, if you look right here, this spot right here, when it goes back to 0, when the height is 0, when the height is 0, this is hitting the ground. Right? This shape tells us that we are calculating a quadratic equation and the ball will eventually come back down. Right? So this is what it tells us, right? We're describing the shape of the graph. We estimated these numbers, and you can look on your own notes for these numbers. The last question is what domain is appropriate, right? Well, it can't be a negative number. You can't have negative seconds. You don't think back in time and figure out where it was. And you can't have past when it hits 0, right? Well, at that point, it's not digging into the ground. So the domain, which is the x values which are appropriate. Probably was really close on this word. All right, which was appropriate. You're not going to have, there are no negative x values, and nothing past the touchdown point, right? When the height reaches 0. You could do the same experiment if you threw a ball up, right? When would it hit 0? Well, the height is 0 when it falls back down on the ground. That's how it works. That's what we're calculating. All right. So at the end of that lesson, the idea was that you can look at this equation, right? You can recognize when the tallest point is. So in this equation, we haven't done this one yet. This is this equation up here. We know that 5 is referencing where it's starting, right? We know that if we look, I'm using my circle button here. So if we look at 5, 5 is referencing how high it starts at. 60 is referencing the velocity of, this is an object, so you're throwing it, right? And then minus 16t squared. Whenever you see this 16t squared, you need to be thinking gravity. So this is resulting in gravity. The result is this upside down parabola, so that we can say, here's where it starts, here's where the max point is, right? This is where the maximum height at about 2 seconds, and then it will land on the ground just before 4 seconds, maybe 3.8 or something like that, right? You're going to have to estimate it because it's not landing exactly. But that's how we estimate, and that's how we use this graph. All right, I'm going to end the video because I think you understand this, but be sure to replay this if you're not sure.